Okay, so in this problem we want to find the slope and displacement at point B. That's out here on the free end. That's a pretty important point because you probably can guess that in a cantilever structure like this, that this free end is going to be the place where you're going to have the biggest displacement. So this would be a good point for that. And also I gave you a value for E, 30,000 KSI. That's roughly steel. And it has an I value of 800 inches to the fourth. Now, if we try to do this with direct integration, what will we have to do?
Break it into two.
Yeah, we'd have to break it into two components, right? Now, on this first side, we would have two conditions. So we would be able to get those conditions pretty quickly, right? Because at A, I know the slope is what? 0, and the displacement is 0. Now, on this right side, I don't have any conditions, right? But I do know that the slope and displacement where the two would meet, section 1 and section 2, would have to be equal. So you're probably going to end up, this might not be a terribly horrible problem to do with direct integration, but you're going to find out that the way we're going to do it here, I think, has an advantage if you're just looking for the value at a single point. So what's the first step in conjugate beam method? What do we need first?
You need a moment diagram.
We need a moment diagram. So let's draw a moment diagram. So what I'm going to do is at A, I am going to assume that I have positive shear at A and positive bending moment at A. And then I'm going to find those values. So if I sum moments at A, I should be able to find my moment at A. So summing moments at A, using, this is statics now, what kind of moment is this in my statics equation? It's a, no? Negative. So that'll be the moment at A, and then about A, what kind of moment does this 5 kip force create? Negative. I know it's early. So that says that the moment at A is going to be negative 75 kip feet. Does it make sense that that's a negative bending moment? How do you think this beam is going to behave when it's loaded? It's probably going to bend something like that, right? So we're probably going to expect that the displacement here is going to be what? Positive or negative? Negative. And we're going to expect the slope to be what? Positive or negative? Negative. And you look at that, that's kind of a frowny face. Concave down, so that's negative moment. That makes sense. While we're here, let's go ahead and get the shear force, which shouldn't be too challenging. It's only two forces. My shear force is acting up, BA. My load is acting down. So it looks like the shear at A is 5 kips, positive shear. So let's draw a template for our shear moment diagram. There's the left and the right edges, and then there's a load applied right in the middle. That's probably a point of interest. And then let's go ahead and scribble down positive x-axis, positive shear. All of our units will be in kips. So what is the shear at A?
5.
We found it. It's 5. What's the change in shear from A to the midpoint? Yeah, it should be the area of the curve. There is no area of the curve, so it will stay 5. What kind of curve is this between here? Well, remember, the slope is given by the load. The load is 0. So here's a curve with 0 slope. As I move from the left side to the right side, what happens to my shear? It changes by negative 5, so it goes from 5 to 0. And then, of course, the change in shear on the last section would also be equal to the area of the load curve, which is 0. We're done. So now let's draw the moment diagram. Positive x, positive moment. This will have units of kips and feet. What is the bending moment at A?
0.
No.
Negative 75.
Holy cow. Mr. Van Tilburg, where are you today?
Oh, no.
Somewhere. There it is, minus 75. The change in moment over the first 15 feet is the area in the shear diagram, which is 75. And it's positive, right? So negative 75 plus 75 is 0. The slope is equal to the load, the shear, which is positive and constant. So there's our shear, there's our moment diagram.
Which is 5.
What is 5?
Slope.
Correct. Positive or negative?
Positive.
Excellent. You're back with us now. And the change in moment over the last 15 feet should be there in the shear diagram, which is 0, and we're done. So there's our moment diagram. Any questions about that? All right, let's draw the conjugate beam. So remember we talked in class way back on Tuesday that in the conjugate space, a fixed connection is free and a free end is fixed. So we would get a structure that looks like this. Now what I like to do is I like to take the moment diagram and pick it up and just draw it right on the beam. So far, I hadn't really had to think. I just transpose this thing. I just pick it up, transfer it right over there. Boom. Now, I do have to think now. What kind of moment is this? Positive or negative? So negative moment becomes a negative load. Which direction is negative load? Down. And what is the magnitude of the load here? It's the moment divided by EI. So I'll have 75 kip feet divided by EI. Now that's my new problem, my conjugate beam problem. And what do I have to find in my conjugate beam problem? Well, I'm looking for slope and displacement at B. What's that going to be at B in the conjugate beam? Shear and moment. So I'll come over here and I will draw my positive shear force at B and my positive bending moment at B. And all I have to do is find those values. So the first thing I want to do is I don't want to deal with this. This is a pain. So I'm going to make that a concentrated equivalent force. I'll just call it F. And I'm going to try to figure out the distance D from the supports to that place. So first, what is F? Well, it's the area of the curve, right? Yes. And that is 1/2 the base, which is 15 feet, times the height, which is 75 kip feet, divided by EI. And what is that equal to? Someone else?
2,250.
Say that again?
2,250.
That seems high.
Yeah.
The I is in 50.
Did you divide by 2? Did you divide by 2?
Wait, are we plugging in E and I?
Oh.
No, don't plug in E and I. Leave it hanging on. If not, it's going to be a teeny tiny number.
552.5.
I like that.
Yeah, I kind of multiplied it.
552 point what? 5? Anybody else get that?
I got 562.5.
Okay, that sounds more reasonable. And that's going to be kip feet squared over EI. So a little bit of bookkeeping here. Now what's D going to be? Well, the distance from here to here is 15. And then I'm going to what? Take 2/3 of that. So it's going to be 15 plus 2/3 of 15, which is 25. So now I just check equilibrium. So I'll start with summing moments. And we'll sum moments about B and make sure it's in equilibrium. So with using our statics equation and right-hand rule, what kind of moment is this on the right-hand side? Positive. Thank you. And this force is going to create what kind of moment about B? Positive. And it will be the force, which is 562.5 kip feet squared divided by EI, right? Times what? 25 feet. So what is the moment going to be equal to? It looks like it's going to be negative, and whatever that times that is, probably a pretty big number now. Maybe somewhere around 14 something. What is it?
14,062.5.
14,062.5. Oh, I've run out of room. That's going to be kip feet cubed over EI. I shouldn't have shoved it in there that tight. Sorry. We'll come back and straighten it up here in a second. And then to find my shear force, I'll simply sum forces in the y direction. So looking at the y direction, my shear at B is down. My force is down. 562.5 kip feet squared. So it looks like my shear at B is equal to negative 562.5 kip feet squared divided by EI. Now, in some problems, if I just say EI is constant, you're done. There's nothing to be done, right? Now, we can check a few things. When we first started, what did we think the sign of the displacement was going to be? It was going to go down negative, and we got a negative value. What did we say the slope was going to be? Negative, and we got a negative value. So at least we're going in the right direction. So now that I've given you an E and an I value, we need to convert those. So remember that moment really maps to displacement. So that means my displacement is going to be minus 14,062.5 kip feet cubed. And now I'm going to divide by E and I. So I'll divide by E first. That's 30,000 kips per inch squared. Then I'll divide by I, which is 800 inches to the fourth. It looks like my kips cancel. This makes that a 2. So it looks like I've got cubic feet over cubic inches. No, I did something wrong. No, that's right. Cubic feet over square inches. So I'm going to convert to cubic feet. So I know that 1 foot cubed is 1,728 inches cubed. And now if you look at it, I should just be in that foot cube gets that foot cubed. I've got cubic inches over square inches gives me inches. And what's that number? It's going to be less than 1, I think. Wow. How many engineers does it take to make the calculation? Seems none. What'd you get?
1.01.
1.01. Anybody else get that? You got that? So that'll be negative 1.01, and that'll have a unit of inch. About 1 inch. We know the shear at B in the conjugate beam matches to the slope in the real beam. And we computed that as also negative, and that's 562.5. Now this is kip feet squared. So we're going to have a similar conversion here. So
So when you divide by E, you still get 30,000 kips per inch squared. I is still 800 inches to the fourth. And see, kips still cancel here. Square inches goes square. So I've got feet squared over inches squared. So I have to convert that. So I want 1 foot squared is 144 inches squared, 12 squared. And now you'll see that is dimensionless. What's that going to be? It should be pretty small. This is going to be an angle.
I got negative 0.0037.
0.0038?
Yes.
Anybody else get?
0.0034.
Okay. Anybody else get that?
Yes.
0.0034, and that will be in radians. So both those values, I think, qualify for small and should be well within the elastic beam theory limits. Any questions about that? I think you can see in review that if you can't draw the moment diagram, you're getting off to a bad start. But if you can, then after that, it looks complicated because of the units and the numbers get a little big. But really, it's just pretty simple. It's just statics. Any questions about this one? All right, I will stop.